So actually, everybody might find this story kind of interesting. It's a bit nerdy, but it kind of fits a little bit with the larger reality of what you're learning. So so the story goes, I finally decided to ditch my like 84-year-old regular cell phone and get a smartphone, and I got like a used Droid X. It's a couple years old. My understanding is that like a couple years ago, this would have been like a pretty high-end phone. But whatever, it suits my purposes to a T. And it came, and phone's awesome. I mean, this is like faster than probably like a computer that I would have bought like 5 years ago. Except that the Wi-Fi sucked. Like I couldn't, like basically I could only get a Wi-Fi signal if I was literally sitting next to the router, and I couldn't figure it out for the life of me. So I did some poking around on the internet, and I discovered something really interesting. So I bought it used, and the person I bought it from had shipped it with an extended life battery, which was a little bit bigger than the original battery, and I think more importantly it was like a little bit thicker, and so probably like the back of the battery was in contact with the cover. And somehow that like ruins the reception on the phone. Like it creates some sort of electromagnetic loop, and it just shuts everything off. So, and it even says, like on the cover, it says only use this battery door with this battery model, and that wasn't the model that it shipped with. So I went on eBay. I got to buy a new battery, $4 including shipping. Okay, it's got a little less battery life than the extended one it shipped with, but now I can use, now the Wi-Fi actually works, and I think the GPS works a little better too, and and even like the 3G antenna. But it was like an interesting lesson because, it just got me thinking about like the pros and cons of like when engineers design stuff, right? So like on the one hand, like if you think about like an iPhone versus like this Android phone. In the iPhone, they just take care of all of it for you. Like you can't open it, you can't mess with the battery, you can't mess with anything. It just works, right? Which is awesome. But the downside is when that battery stops holding charge, you're done. You got to send it back to them, $100, whatever. Like you're just at their mercy. Whereas in this case, you can, you can get a new battery for $4 shipped. But, you have to take responsibility for the fact that you might get a battery that ruins your Wi-Fi and then have no idea what happened. So it's just kind of like an interesting, when you think about designing product, you think about trade-offs, right? I mean, there's a whole usability thing, but holy cow, that comes at a price. So anyway.
I mean, the same thing tied to the computer something before. You design all these features, but what are you going to gain at the end of the day if you got rid of?
Right.
Featuring too much could also affect the signal you're dealing with.
No, that's exactly right. I mean, there's very rarely any instance in engineering where you're getting something for free. It's like if you get yourself more of one thing, it costs you more of something else. And what's kind of cool about it is that there's really no right or wrong answer, right? It really just, like at some point, this is why when we get to senior design, we really harp on this thing about, like, senior design isn't just about making something, right? I mean, you could make something, but that doesn't make you an engineer, right? And senior design is about engineering something to meet a design constraint. And, before the engineers ever get involved, like somebody sits down and says, okay, this is what the features have to be. This is the price that it has to sell at. Like you ever go to IKEA and you see those signs that say, like we decided that this table would cost $19 before we even designed the table, right? Like if you can't design it so that it fits in a box this big and it lies flat and it weighs this much, because we have to ship it and that fits with our business model and it has to sell for $19.99, those are the design constraints, right? If you can't make it, then we don't want it. If you have to make it out of particle board or whatever, then make it out of particle board. But like that's what the deal is. So senior design is all about coming up with design constraints that make sense and then making whatever engineering decisions you need to actually meet those design constraints. So it's really more about like making the engineering decisions to meet the design constraints than it is about actually making something. Because anybody can MacGyver something, like yeah, a little of this, little of this, little of that. Like you make something work, but that's not really the same as saying, I set out to make a product that would sell at this price, that would have this transmission range, that would have these features, and then I had to make some tough decisions in order to make that happen, and then this is the result. So anyway. Food for thought. I have a working cell phone now, so I'm pretty excited about that. All right, so next thing you need to know is, you'll be happy to hear this, I'm canceling Wednesday's class. It's not by choice. I'm actually I'm not thrilled about canceling class, and I may come up with some alternative activity that I'll put online or make you read or something. But due to things outside of my power, I cannot be in Philadelphia on Wednesday. So there we go. Go family stuff.
It's important.
Yeah, it's whatever. Yeah. So anyway, don't come to class. I won't be here. But you know.
I would actually like to change my response. I'm disappointed.
I like that guy. All right, yeah. So be disappointed, but like I said, I may send out some reading or something because we don't have a ton of classes left, right? There's one full week after Thanksgiving, and then it's the last week of class.
Yeah.
Is that right, or did I miss a week?
Yeah, that's right. Yeah.
We have until January, right?
What's that?
We have until January.
You have until January, yeah. I want you to come here on January 5th for your final. No, I'm just kidding. No one will be here. So yeah. So what do I need to cover from Friday? What did John make a mess of things, or did he do a good job?
Can you just do that impulse train thing?
The impulse train. Fourier transform of an impulse train is an impulse train. All right, watch this. All right, watch this. Can we all agree that this is an impulse train? T, 2t, 3t. If I want to look at the energy content of the signal, what is the appropriate thing that I should do? Fourier transform or Fourier series? Series. Why? It's a periodic signal. Can we agree on that? It's periodic. You concur. Thank you for concurring. At what frequencies will we have harmonics? What will be my omega sub n? 2 pi n over t, right? 2 pi over t is the first harmonic, and then times n gives you the nth harmonic. Okay, now we have to figure out how much signal we have at each harmonic, right? This is the locations of the harmonics. Now we actually have to figure out how much stuff I have at each harmonic. Okay, so the formula reads a sub n equals 1 over t integral over 1 period x of t e to the minus j2 pi n over big T, little t, dt. Aren't you glad we're done with this? Okay. Let's see. This is 0. This is minus t, minus 2t. Okay, so how do I integrate this thing over 1 period? What should my limits of integration be? Well, 0 to t is hard because then my impulses fall right on the limits of integration. I don't really know what to do. How about I make life easy for myself and I make my limits of integration minus t over 2 to t over 2. Can we do that? Okay. So now I'm going to integrate from minus t over 2 to t over 2. So now let's look what's inside the brackets, inside the integral. So x of t is 0 everywhere except for 0. So look at what's going to happen to this expression. X of t is 0 everywhere except for where t equals 0. So where t equals 0, what happens to this exponent?
Just becomes 1.
That just becomes 1. Okay, so now I'm integrating x of t, which is an impulse, scaled by 1. And what's the integral of an impulse? By definition! 1. Okay, so all of this equals 1 over t. Okay, so let's draw our Fourier transform, our Fourier series. Yeah, so watch this. Okay, where's my first harmonic? 0? Good. What is a sub 0 according to that? 1 over t. Where's my next harmonic?
T. 1 over t times 2.
Yeah, it's this guy, right? 2 pi times 1 over over whatever t is. Okay, so it's over here. 2 pi over t. What's a sub? So that's that should be omega sub 1, right? What's a sub 1? What's a sub 1 from our integral? 1 over t. What's a sub 2? What's a sub 3? Get the picture? Fourier transform of an impulse train is an impulse train.
Is it spread further out or is it closer together?
What do you mean, why does it spread further?
Just drawn onto scale.
Yeah, I mean, like, why is it more stretched?
No, he said that, like, as the time goes on, the Fourier transform of the impulse train, like, expands.
Oh no,
He said the distance between.
no, he said it didn't. He made a mistake and he said it didn't.
Well, it's inversely proportional to your period.
Yeah, the harmonics are going to be evenly spaced. What he may have meant was that as t gets smaller, like if you make t smaller, so the spacing between these gets smaller, then 1 over t gets bigger and the spacing between these gets larger. That's probably what he meant. Okay, so then did he do the thing where, so he said that when you sample, what you're really doing is multiplying a train, like an impulse train, times a signal, right? And so when you multiply in the time domain, what do you do in the frequency domain? Convolve. And so in other words, in the frequency domain, I'm going to take the Fourier transform of x, which I'll draw like this, and I'm going to convolve it with this impulse train. How does it work when I convolve with a bunch of impulses?
Copy at each of
Just like your quiz, right? Convolving with an impulse just takes your thing and copies it at the impulse, right? So that we should have learned during the convolution portion of your class. So let's see. This was at 0. This was at 2 pi over t, and so on. And how do we avoid aliasing? Oh, and let's say our signal is, we call it band limited. Okay, so let's say it's got the signal is band limited. Your original signal means it's capped at the highest frequency it has in it is B for band limited.
Period has to be bigger than 2b.
Right, exactly. So as long as these guys don't overlap, I'm good to go. That means I've sampled at a high enough frequency. Okay, so under what conditions will it be that those two don't overlap?
Nyquist.
In order for that to work, B would have to be less than the halfway point. And the halfway point is half of this, which is pi over t. Can I rearrange that a little bit? This is my bandwidth in hertz or radians per second? Why don't we do it like this? Can I rewrite it like this? 2 pi b. So now b is in hertz. Now b is my bandwidth in hertz. That way everything will cancel a little cleaner. So if I do this, the pi's cancel. And I'm going to find out that b has to be less than a half of 1 over t. And what's another word for 1 over my sampling period t? Sampling frequency. And there's Nyquist. So it's the same conclusion we reached. We've sort of looked at this two ways, right? The first way we did was we looked at discrete frequencies, and we decided that the discrete frequency omega had to be less than pi. Because once the discrete frequency omega got to be bigger than pi, then it would start to repeat itself again. Okay? Bless you. So we decided that omega had to be less than pi, and that led us to Nyquist. And now I'm giving you a different approach. We're looking at the Fourier transform, and again we find out that bandwidth has to be less than pi. Or sorry, the Nyquist theorem has to hold. It's the same thing. So if I make t smaller, what do I do to fs?
Increase it.
Yeah, if my sampling period gets smaller, my sampling frequency gets bigger. Okay? So if my sampling frequency gets bigger, I can accommodate higher frequencies in my signal. So if you have a low frequency signal, you need a low sampling frequency. If you have a high frequency signal, you need a high sampling frequency. All right. And what do we learn happens when you undersample? Aliasing. And what does that mean? I mean, aliasing is that's right. That's the right word. But what is practically what happens when you alias?
You lose the signal to something else.
Signal
Right.
is for a second signal that's not misinterpretation.
Right. The signal becomes misinterpreted. That's exactly right. If you go through in the book, I actually give you a method for calculating. I don't think I'm going to do it in class today, but you should read it. I actually give you a method for calculating, like what the miscommunicated frequency winds up looking like. So in other words, if you take a 1,000 hertz signal, if you take a 1,000 hertz cosine, what's the minimum frequency you have to sample it at? 2,000 hertz. Okay. So in the book, we do this calculation. Like if you have a 1,000 hertz signal, but instead of sampling it at least 2,000, you sample it at, let's say, 1,800 hertz, you can actually calculate what the observed frequency will be, like what that 1,000 hertz signal is going to look like once it's sampled. I can't think of it off. It'll look like, I think like an 800 hertz signal. Okay, so anyway, so it's just a miscommunication. You have to hit at least Nyquist. Now usually we go more than double. Yes?
But that's when you want to go from analog to...
Digital. Exactly. That's what we're doing. We're sampling our signal. Right? Because, when a computer looks at a signal, it's just a list of numbers. Right? That's just how computers work.
So pretty much an analog to digital converter will be rated like that?
Yeah, pretty much. I mean, an analog to digital converter has a number of things on it, but one of the parameters you can set is the sampling frequency. The other thing you can set is the resolution, which I don't want to get into. Like basically, how many bits of resolution? Like if you think about digitizing a signal, not only do you have to make the time axis discrete, but you've also got to make the y-axis discrete as well, right? Because a continuous time signal, the y-axis is discrete, right? There's infinite y values that your signal can have. But again, in a computer, you're constrained, right? If you're representing your numbers as double precision floats, there's only so many values your double precision float can take, right? So not only are you discretizing the x-axis, but you're also discretizing the y-axis. Discretizing the x-axis is set by the sampling frequency. Okay, so if you increase the sampling frequency, you have a finer resolution on your x-axis. The y-axis is discretized according to the number of bits. So let's say you do a 16-bit A to D conversion. What that means is that you're going to take your available y-axis and divide it into 2 to the 16th boxes. Okay, and at every sample, you're going to decide which box of those 2 to the 16th your signal falls in at that time. And then that's what gets reported is the box number. Yes?
So like the piano notes, right? When we reduce the window,
Yeah.
Technically didn't we sample?
The signal was already sampled.
Well, if you reduce the window, some window.
That's a little different. That's different because you're clustering samples together in that one. It's sort of, it's the same concept, but it's not really the same. It's the same, the math works the same, but conceptually it's different. Yeah.
I burned a CD before, and I went to change the lines or wherever, and I changed the video to straight CD.
Yeah.
And then I tried to play it it played on the laptop, but when I took it in my car, it didn't play.
Yeah, well that just depends on, these issues are really interesting, right? Like if you think about a signal, okay, so I guess we're going to get off on a tangent now, but that's okay, these are fun. So when you discretize this signal, the way I've drawn it, it's continuous in time, and it's continuous on the y-axis. We'll call that x of t. So what I was saying is, typically the way an A to D converter is, the first thing you do is you define a range. Okay, so let's say 0 to 10 volts, just to make the math easy. Okay? And then we're going to have a number of bits. So let's have a really lousy A to D converter. Okay? Actually, let's make this even easier. Let's make this 8 volts. Okay? Because I can tell where the math is going to go. Okay, we'll make this 0 to 8 volts. Let's have a 3-bit A to D converter. Is that a good A to D converter? No. Okay, that is craptastic. You should expect better. Okay, but it'll work very nicely. If you have a 3-bit A to D converter, then so if we have 3-bit, then what you really have is 2 to the 3 levels. So you're going to go all the way from 0, 0, 0, 0, 0, 1, 0, 1, 0, all the way up to 1, 1, 1. Okay? So here's 0, 0, 0, 0, 0, 1, and so on. So basically what you're doing is you can think of making a grid like this, and then a grid like this. Okay? So let's see. If I've got if my range is 8 volts, and I've got 8 boxes, how many volts does each box represent? 1 volt. Okay, so box 0, 0, 0 represents 1 volt. That's your resolution, 1 volt worth of resolution. Usually you want like a millivolt or a microvolt or some kind of impressive resolution. Like a volt of resolution is lousy. Okay? But essentially what you're doing is you're saying, okay, in the first sampling window, what's the value of my signal? Is it in box 0? No. Is it in box 1? Yes. Okay. So the first sample that you're going to record is 0, 0, 1. Okay? Then you go to the next window. Okay? Well, what is it in my second sample? It's mostly 0, 0, 1, but a little bit 0, 0, 0, 1, 0, but it looks like this one's going to win. So, okay, so you do another sample of 0, 0, 1. Okay? Which is interesting, because now, as far as the digitized signal is concerned, I had the same sample twice in a row, which isn't really what happened, but that's what you get for using a 3-bit A to D converter, right? If you want a better idea of what's going on, you have to do, 16 bits, and then you'd have all these really skinny lines, and then you'd see your signal go up and down. Okay? Sorry, yes?
No, they actually have things where you can actually Mario, or something pretty much. You can take a normal song and convert it to an 8-bit song.
Yeah.
Something like that.
Yeah, I've heard of those. Those are awesome. Okay, right, and they sound lousy because you're losing most of your signal quality. Right. I'm going to get to Guy's question in a second. I haven't forgotten that. Okay, and then the third one would be 0, 1, 0. Okay, so there's your 0, 1, 0, and so on. And this is actually what comes off the A to D converters. You get this string of numbers. Okay, it's just you need, after the fact, to know that I had an 8-bit range with 3 bits of resolution, so you know that each box represents 1 volt. So if you know each box represents 1 volt, you can then go and convert this number back to volts. Okay, but this is what comes off the A to D converter. Now, you're talking about recording a CD. So CD audio is usually like 16-bit, which is fine. So when you encode audio on a CD, right, it's encoded. So you need the DSP on your CD player has to understand how the data was encoded. Okay, and there's only so many algorithms that get pre-programmed onto it. So, in the early days, it only knew one format, right? Just 16-bit audio sampled at 44.1. And as long as you put in a CD encoded like that, it knows the DSP knows how to handle it. All right. Now you come along and you do a 32-bit. That's totally fine. You can do that, but now you just need to have a machine that can read it. Okay. So you go to your computer. That's easy, right? Your computer is just software, right? The software gets upgraded as often as you need to. You put it in your CD player. Probably you have a nice CD player at home. It has a good DSP. Go to your car. Maybe the DSP in your car CD player is a little outdated. It doesn't know what to do with 32 bits of resolution. But in theory, it would give you better sound quality. Okay. So that's the deal. And you could it goes even further. Like you could put MP3s on there, right? Again, it's just you need to have the chip that's on your audio machine, on your CD player, basically just knows, oh, I know how to play them. I know how to decode MP3s. It's just another file format. Good. So we always sample a little bit more than twice Nyquist. A little bit more than the Nyquist limit. Okay? And here's why. There's always slop. So what are you learning in your computer assignment 4 about filters? Is there such a thing as a perfect filter that cuts off everything exactly after the... Of course not. So here's a typical thing that we do, right? So let's say you start with a signal like audio. And let's say if we look at the if you look at the Fourier transform of your audio signal, it looks like that. And there's a lot of stuff there. There's audio, but then there's some noise as well. Like there might be some white noise. What's white noise?
Horrible.
Horrible.
Filter.
There's a specific property of white noise.
All frequencies randomly distributed.
What is white light?
It contains
All frequencies. What is white noise? Noise that's at all frequencies. Okay? It's awful because it's at all frequencies, right? It just goes on and on and on, right? It's just there. Okay? So, if I want to take this signal and sample it, so let's say this is my 20K, right, where my hearing finishes. Okay? I mean, you know, we're all out of our teens now, I'm guessing. I think everybody's out of our teens, right? I mean, it's, you know, you probably can't hear up to 20K anyway. You know, I'm in the second half of my 30s. I probably could like cut out at about 15K now. But anyway, so what am I going to do before I sample this thing to avoid aliasing?
low pass.
Right? If I sample this thing now at 44.1, I've still got stuff out here. That stuff will alias. Right? So the standard trick before you filter it, before you digitize it, is you filter it. Okay? So you stick it through a low-pass filter. Roughly speaking, what should be the cutoff frequency of my low-pass filter? Yeah, I mean, again, now you can start to talk, right? You maybe use a Butterworth filter or a Chebyshev or something, right? If audio quality was really important to you, which kind of filter might make more sense?
Butterworth.
Yeah, Butterworth is flattest in the passband, which means it's going to warp your sounds as little as possible. So you build some sort of filter, and it cuts off. Okay? So that's going to get rid of those higher frequencies, which is good, because if you don't get rid of them, they will alias. So when you use a low-pass filter like this, it's called an anti-aliasing filter. Okay? It removes the frequencies that would otherwise alias. All right? And then you sample. Again, even if I put my corner frequency at 20K, I don't just want to double that and go to 40K. I want to put a little slop on there. Why? Because I didn't build a perfect brick wall filter. Right? Did my filter perfectly get rid of everything above 20K? No, there's always a little bit left over. So you always go a little extra just to be on the safe side. Okay?
Is there a relationship at all, or is that just something you have to determine kind of like experimentally?
Yeah, it's a little bit rule of thumb. I mean, different people do different things. And it really kind of depends on the application. I mean, I would say if the sample, you know, double your bandwidth is probably not enough. Triple is probably too much. I mean, like 1.5, 1.25, like over Nyquist is probably reasonable. But typically that's what happens. And there you go. So that's there's your kind of like sampling theory in a nutshell, and it works really well, right? So I had something I was just going to tell you. It was really cool, and I forgot. Did I really just blank? Yeah, I just blanked. Okay, maybe it'll come back to me. So, no, it was cool. I want to tell you. It's at the tip of my tongue. 20K, we talked about anti-aliasing. We said you get rid of the stuff that would otherwise alias. Anyway, we'll come back to it if I remember. What's that? Down sample, up sample.
I don't remember in the next
Dissemination guarantee.
Yeah, it wasn't that. Oh, okay, I'll come back to it in a minute. So, what I do want to talk about briefly now is once the signal is sampled, how you understand what you've got. So, let's look at this signal for a minute. So we've learned that signals and systems are the same things, right? I could show you a continuous time signal and say that's a signal. You can take its Fourier transform to see what frequencies it has energy at. Or I could say that's a filter, right? You can convolve with this, with that impulse response, and you could find the frequency, that you can think of it as a filter, right? So any signal can either be thought of as a signal or as a system, right? A filter. So we're going to think about this. We're going to look at this signal or filter, and I want to think about what's the frequency content of that? Is that a high frequency signal? Is that a low frequency signal? How can I figure that out? Every other sample is 0, by the way. Two sticks. Nope.
Well, we're in like a sample.
The sample domain kind of the same as time.
Okay, use that as an intuition. I remember what I was going to say. We're committed now. We're doing this. No, actually, I'll tell you briefly what I was going to say. If you play video games, especially on your computer, you may have come across this concept of anti-aliasing for your monitor.
16x.
Do you ever wonder what that's about? Here's what it's about, right? Okay, let's screw this. We'll come back to this later.
Well, this is like spatial for
yeah, and it actually fits in very nicely with your computer assignment. So your monitor is what? Your monitor is a series of pixels, right? And what's the rule with pixels? Like basically, how does a pixel work? Red, green, blue. But the point is, each pixel has one color, right? That's it. It's like every pixel is either red or green or purple or orange or whatever, but it's one color. So you come along now, and you want to display a picture, okay, for your awesome video game that you're playing. But let's say that picture, so let's say the picture you're trying to, let's say this is the picture that you're trying to render on your screen, okay? And the features of this are smaller than the pixels, okay? So if I superimpose, let's say there's a face, and let's say here's an eye, okay, on the face. So I want you to think of this as sampling. This is the continuous time signal. And when I try to display it with these pixels, I'm effectively sampling it, aren't I? Okay, what's my sampling rate? Or what's the equivalent of my sampling rate? Right, it's basically the spacing of the pixels, right? If the pixels are smaller, I'm effectively sampling this at a higher rate, okay? How many pixels do I need in order to properly represent this? What's my equivalent of Nyquist? Yeah, basically you find your smallest feature here, okay, and you figure you need at least 2 pixels to cover that smallest feature. Now, what happens over here when you have this? What happens if I have this picture? Like, what's going to happen with this eyeball that's all supposed to be, that's got different colors?
No,
right.
One whole pixel is going to be white or something.
Right, exactly. It's going to look choppy because one whole pixel is going to be white and the next one's going to be black, and it's not going to look like an eyeball. So what happens is that, this is obviously a dramatization, but essentially what happens is that your computer runs a layer in between called an anti-aliasing layer, okay, that basically, before it sends the image to the screen, it basically takes this and smooths it, okay? It filters it. It tries to say, okay, yeah, I know there's a hard edge on this eyeball, but why don't I smooth it out a little bit so it's like dark and then it like kind of grays out in a bit more of a spread out fashion so that when I render it on the screen, it'll look nice on the screen. Because otherwise, effectively what I'm going to have is aliasing, right? It's just going to, which you'll just perceive as, it looks awful, okay? There'll be like pixels that look, things that are supposed to be round that look blocky, or things that are blocky that are, it just won't look right. And you won't even be able to quite put your finger on why it doesn't look right. Same thing with audio that's been aliased. You can't say, oh, I clearly hear that 1500 hertz tone and, it should be at 2000 hertz. It doesn't work like that. It doesn't sound right. So same thing. So effectively what they do is they smooth the image. Okay? They smooth the image to the point where it can be represented cleanly on your monitor. Yeah?
What I was going to say is with like 3D graphics, if you're rendering it, I think what they do is they'll render it like several times higher than the target resolution, and then they'll average it.
Right.
So,
Yeah, I mean, there's all these tricks you can play to kind of beat the system. Yeah.
is that equivalent to something called dithering in the audio space, or?
I think so, yeah. I don't know a ton about dithering, but I think that's roughly correct.
Okay.
Yeah.
Is
Yeah.
that the same thing, like when you're watching a video, you download a video, and you're playing with the 4:3
Yeah.
aspect ratio, and then when you move to 16:9,
9.
and then it just gets so blurry, you can't really see a thing.
Yeah, what you're doing in that case is you're basically making the pixels bigger. It's like the same pixel, but now you're stretching it out. So of course it's going to look lousy. Yeah. Yeah, there's all these cool, I mean, there's so many interesting things about this. Did you ever see the thing about the, did John tell you about the thing with the like when you see wheels on TV that look like they're moving backwards?
The windmill or the wagon wheel effect?
Yeah, the wagon wheel effect. That's sampling as well. You ever wondered like why you see on TV wheels moving backwards?
There's some kind of standards now in factories where they have to use 3-phase lighting, because if they use a single phase, then it can make things spinning at 60 hertz look like they're stationary.
Oh, that's cool. Yeah, I mean, effectively what happens is, like, let's say you've got a wheel that's rotating in this direction, right? So now you've got a camera taking pictures 30 frames a second. So suppose you take a picture here, all right, and now the wheel's going to rotate, and you're not taking pictures fast enough, okay? So the next time this spoke has gotten to here, let me draw it a little bit more obvious. Okay, so now this is the next image. Okay, so if you see this image and this image, which direction does the wheel look like it turned? To the left or to the right? To the left. What's the problem? It's aliasing, right? You haven't sampled high enough. You're taking pictures not often enough. Right? If you'd taken a picture in the middle, right? If you'd taken a picture in the middle, you would have seen something that looked like, maybe like this, and then you'd have said, oh, this spoke is now here and is now here, and then it would have looked like it's rolling to the right. So you increase your sampling rate, the aliasing goes away.
It's like it takes the picture whereby it takes it by the frame, but then it kind of aligns it together and you see every bit of it.
Oh, like a panoramic?
Panoramic.
Yeah. There's another one that's really cool. Another really cool example. Is this a good example? Let me think for a second. Yeah, like sometimes, I think this is right. I hope I'm not screwing this up. You ever see pigeons like bob their heads? Yeah. They're spatially sampling, right? They're upsampling, right? When a bird takes a picture, people try to do the same thing with cameras. Like if you take a picture, like people basically try to beat. This is how people try to beat low resolution camera problems for a while, and I think birds basically do the same thing. Like let's say you only have 9 pixels in your camera. It sucks, right? It's a lousy camera. Okay. What you can do is instead of just taking one picture, you can take one picture, and then the next instant shift it a little bit to the right, and then a little bit to the left, and then up and down, and take like 9 pictures in really, really fast sequence, and essentially you're taking your 9 pixels and you're upsampling, right? You're just kind of taking all these different pictures, and then you can sew them back together with software on the back end and effectively raise your sampling rate. So you can actually have a 9, even though you only have 9 imaging elements, you can actually wind up with a 64 pixel image. Okay.
You said that's what pigeons do?
Yeah, well, when pigeons bob their head, they're effectively, taking a picture here and pigeons, when their eyes are on the opposite sides of their heads, it's different. I used a bad example. We have depth perception because we have 2 eyes looking at the same thing, so we have a slightly different image, and we can estimate depth. Pigeons don't have that. Their eyes are on opposite sides of their heads, so they don't have that. But what they do is they bob their heads, and then their eye is effectively in 2 different places, right? and then they use that difference to estimate depth. It's sort of like a sampling issue. I mean, it's using multiple images to give you more information than you would have had with just one image. It's a little bit of a stretch.
Back to the wagon wheel thing, like would the equivalent of anti-aliasing that be motion blur? Like if you motion blur it.
Yeah. But that blur then would be giving you enough information to sense that it's going in the one direction versus the other. Yeah. Pretty cool.
One other thing.
Yeah.
Like if you're watching CNN in high definition.
Don't do that.
And
it's bad
the
enough
ticker is moving, when the TV refreshes, the image gets blurred. Like the ticker, it gets blurred, it gets distorted. Why does it do that?
That probably has more to do with like the quality of the data that's streaming. That's probably more to do with like the way the data is encoded and the way it's streaming and so on. I don't know that you could sort of blame that on an aliasing issue. I mean, presumably on their end, it was all very nice and crisp. It's just the delivery.
It's another form of aliasing, but it's for image compression though. So it's aliasing where your compressed image isn't matching up right to your actual signal.
Let's do this real quick. I've got 9 minutes left, and I want to make sure that we at least have this conversation. Okay, real quick. If this was a continuous time signal, what would it look like?
Something like a square wave.
Yeah,
Zero
right.
everywhere.
Right. If it was a continuous time signal, I'd basically be looking for something like that. Okay. Is that a low frequency signal or a high frequency signal? It's high frequency, but if I take the Fourier transform of this, what would it look like? Sync pulse. Okay, so sync pulse looks like this. Is most of the energy at low frequencies or high?
Low frequency.
Low, right? Here's 0. Most of the action is close to 0. It's mostly a low frequency signal. So, I anticipate if I were to take the Fourier transform of this, I should get something that tells me basically the same story, that this is mostly a low frequency signal. Okay, so I just want to throw this out here. In the same way that we have a Fourier transform for continuous time signals, we also have one for discrete time signals. And it works like this. X of discrete time frequency omega is equal to, now I can't do an integral because I don't have a continuous signal anymore. So instead I'm going to do a sum over all points, and it's x of n. That's the same. I mean, I'm writing this basically like the Fourier transform integral. Instead of x of t, I have x of n. And instead of e to the j omega t, I have e to the negative j omega n. The end. Should we try? Okay. So let's take the Fourier transform of that guy.
Would it be times dn? Or some differential n? No?
No. It's good.
Well, it's because it's an impulse train, right?
Yeah.
Okay.
Okay, so let's try it with our signal. So how many elements are going to be in my sum for the signal I have on the board there? Just 2. So I've got n equals 0 and n equals 1. Okay, so let's start with the n equals 0 term. So x of n equals 0 is, what's my x of n for the first term? 1 e to the minus j omega, and my n is equal to 0. Okay, so that's it. That's the first term. Now I'm going to do the n equals 1 term. Okay, so x of n is 1 e to the minus j omega 1. Okay, and I'm done. It does look kind of like a cosine. You might be onto something. Let's massage that and see what it looks like. So ordinarily this is enough. Like just put it into a computer and plot it. In fact, I've got 5 minutes. Let's just do it on the computer. I can show you how to massage the math to prove it's a cosine, but it would take the full 5 minutes and it would be kind of lame. Just gotta find my little doodad. You just be patient and see. It's going to be cool. It's not an infinite cosine. Yes, sir. It is a shifting. Okay. It is 1. Okay. 1 plus e to the minus j omega. All right, fine. What do we got? We said 1 minus e to the minus j omega plus. Okay. So is that the same as e to the minus j omega over 2 times e to the j omega over 2 plus e to the minus j omega over 2? Can I write that? Okay, what's this nonsense in the middle? 2 cosine omega over 2 times e to the minus j omega over 2. So this is the shape of it. That's the magnitude with some phase shift. So it is it's a cosine at half omega. So let's look at that and see what it looks like. Hello? I'm sorry, I'm going to... Are we looking?
The most, and that fails the most ethically.
Yeah. Detect display. I just have to tell it to detect displays. Yeah. Ha! Some knucklehead plugged it into the wrong one. There's 2 jacks here. There's a monitor and an input. Somebody had it in the wrong one. Take that. Okay. And hey, look at that. My MATLAB is not feeling well. Let's have a look here. Boo. Boo, MATLAB. That was a vital 2 minutes I lost there. Okay, so let's see. Omega equals Lin space minus 20 to 20. Okay, x equals, we said 1 plus e to the minus j times omega. Is that what we came up with? Okay, plot w, comma. Now remember, x is going to be complex because all Fourier transforms are complex. I'm just going to look at the magnitude right now. Now, why am I showing you this? First of all, is it a little... Okay, what's the most obvious thing about it? It's periodic. Did we expect it to be periodic? Yes, because when we sample, what happens when we sample? Remember I just, at the beginning of class, we were convolving the Fourier transform of x of t with the impulse train, and it was getting repeated, and I said as long as the things are skinny enough, they won't overlap. But we were expecting the Fourier transform to be periodic, were we not?
Yes.
Because it's sampled. Any sampled signal has a periodic Fourier transform. With what period? 2 pi. Look at this. It starts out centered at 0. Actually, let me do this. I'm going to relabel my axis. This is a standard trick. I've divided my axis by pi, so when it says 2 here, that really means 2 pi. Okay, so here's 0. Remember how I said the biggest frequency you can have is pi? Look at what happens. Once you get to pi, it starts repeating itself again. Okay, which means that you've got to have, right, your signal is always going to go from minus pi to pi, and then it's going to repeat itself. So when you sample, you have to set your sampling frequency so that everything that you want to happen happens before frequency pi. Otherwise you alias. Any sampled signal will have this Fourier transform. Okay? It will always be periodic with period 2 pi. Now, we hypothesized that we were going to have a low frequency signal. Do we have a low frequency signal? Can I read this graph and interpret that? Remember, we said, okay, so it's periodic, we said minus pi to pi is really the only part we care about, because after that it's going to be periodic. And remember, with continuous time Fourier transforms, we said the positive and the negative frequencies are going to be mirror image. So really the only part we care about is 0 to pi. Right? 0 is 0 hertz, pi corresponds to your Nyquist, half the sampling frequency. So where is all my energy? Is it at low frequencies? It's a smooth transition, but most of the energy is affiliated with the lower frequencies. By the time you get to the higher frequencies, around half the sampling frequency, there's no energy there. Pretty cool. So, I'll leave you this food for thought. Okay, you can work on this maybe for, I don't know, Wednesday, okay, when I'm not here. If you were to take the Fourier transform of this signal, this discrete time signal, is that a high frequency signal or a low frequency signal? It's a high because it changes, right? Up, down. Up, down is a high frequency. It's changing. If you take the Fourier transform of that, you'd better get something that shows high frequency. All I would need to do that is change this from a plus to a minus. And now look at what I have. Do I now have a high frequency signal or a low frequency signal?
High.
High. Look, here at 0, omega equals 0. I have no energy. And then all the way at the sampling frequency, or half the Nyquist frequency, I have high energy. So that's a high frequency signal.
Now, if you improve the resolution of your square wave, would you see more of the sync pulse?
Yes.
So this is kind of like an average of it?
Pretty much. We'll get to that. Okay, have a nice Thanksgiving. I'll see you later. I got to go teach some other people.